You waited for me.
Hello.
Hi, I am very, very sorry. Uh, Bottom line, I had a doctor's appointment that ran late, guys. So I apologize for that. And bottom line, it will affect you later on this semester probably. I've been diagnosed with prostate cancer. I probably will have to take a week or two off in March, probably around spring break. Not a big deal. It's basically the guy told me I'm going to die with the disease rather than from it. So not a big deal. I just wanted to tell you, give you an excuse as to why it was pretty serious, to what reason I was late today. And I do apologize for that. We ready to go, guys? We happy? We ready to go? We anxious?
Well, I'm really sorry to hear that, Professor.
Don't even think about it. We're all good.
Wait, what happened? What's going on?
I have prostate cancer. I just found out just a few minutes ago. It's no big deal. The only reason I even mentioned it to you is that I probably will have to miss a week or two in March around spring break. Not a big deal. We're going to get through this, guys. We're going to get through this class together.
We sure are.
Absolutely. All right. So I'm going to find where I need to be. We have the density. Do we have the density PowerPoint up there?
Yes.
Everybody's seeing the density PowerPoint. I'm going to turn the other light on too.
So he's not in witness protection
Righty,
like last
density.
time?
No, he's not in witness protection.
Not today.
Density, guys. Basically, all we're dealing with density is we are dealing with the mass per unit volume. Okay? That's all density is. It's defined as mass per volume. And when we're dealing with it, if we are looking at things, come on. Now, if you have 1 kilogram of feathers and you got 1 kilogram of rock, Jennifer, which one do you think is going to have the greater volume?
Greater volume would be the rock.
The rock?
Feathers. Oh no, the feathers.
The feathers, because there's not as much weight per volume. So you're going to need much more volume. You're going to need much more volume before you can get the same weight as you have with a kilogram of rock. And that's basically all we're talking about. Density is wonderful because it is a physical property. It is an intrinsic property, which means it doesn't matter how much you have, the property is going to be the same. If you have gold, if you happen to be lucky enough to have a ton of gold, as opposed to a little nugget of gold, each of them will have the same density. That means that we can use density to identify substances. Very, very good quality. How do we know that water and ice have different densities?
Ice floats
Do you know why ice floats?
because it's more dense when it's frozen.
Thank you. No, it's not more dense when it's frozen. It's less dense. That's why ice floats, right? No. All right. But why? Why is ice less dense than water? Anybody have any idea why?
Well, I know that the atoms are moving more freely versus in the solid form of the ice, it's packed more together.
Well, when you have solid ice, is that Hunter?
It sure is.
Okay, Hunter's exactly right. When you have solid ice, you have the ice molecules that are very, very rigid. They can't move. They can't move. And so because they can't move, there is a fixed distance between one ice molecule and the other. On the other hand, when you have water, they can move. They can move real close and they can get closer to one another. Water has something called hydrogen bonding. It is the second most powerful intermolecular force. And intermolecular forces are what make things solids or what makes things liquid. So with it being a liquid, since it's not in that rigid structure, water can slide by and it can get closer than ice can get to one another.
I have a question.
Yes, Hunter.
So the intermolecular force is different than gravity, right?
Yes, the intermolecular force has
Isn't
to
it like-
do.
That refers to a weak force, strong force, right?
Intermolecular forces, if you compare them to intra, which means within the molecule, intramolecular forces are much stronger. In other words, the chemical bonds are much stronger than the intermolecular forces. And this is why it takes less energy to boil water than it does to burn water.
Okay.
We good?
Yeah. Thank you.
All right. Very, very easy, guys. To find the density, all we got to do, find the mass, find the volume. Then, magically enough, if we take the mass and divide it by the volume, we've got the density. Simple enough. Find the mass somehow, find the volume, then divide the two, we have the density. And we have this real handy dandy nifty triangle here. I love this triangle. It's called the density triangle. M stands for mass, D stands for density, V stands for volume. Okay, now you got mass. It's kind of like looking like a numerator. And you got density and volume that are kind of like in the denominator part. So if I have the mass, if I have M, and I have the density, mass is in the numerator part, density is in the denominator. If I have the mass and I have the density, I divide the mass by the density, I get the volume. On the other hand, if I have the mass and I have the volume, again, mass is the numerator, volume's in the denominator, mass divided by the volume gives me the density. The third member of this triumvirate, if I have the density and the volume, those are both on the same level. So in order to get the mass, I'm going to have to multiply the density by the volume. Keep this triangle handy. It makes a whole lot of sense. If the things you have, mass and density, divide the mass by the density, you will get the volume. If you have the mass and the volume, divide the mass by the volume, you will get the density. And if you have the density and the volume, multiply the two of those together, you will get the mass. Make sense, guys? Handy dandy, very, very easy. Density problems are, for the most part, very, very easy because you only have one of three equations you need. You're either going to know the mass and the density to figure out the volume, the mass and the volume to get the density, or you're going to know the density and the volume to get the mass. Somebody had a question.
Yeah, I get that part. It's just it's when you most of the questions they'll ask you, determine the density, but then they want you to put it in the right sig figs. So remembering the right sig figs is the thing. And I notice everything super tricky.
Okay. I'm going to tell you this right off the bat. Sig figs are a bitch.
Yeah.
They are horrible. They're horrible to deal with, but get it now. Defeat it now. Because if you get it and you understand it now, you're not going to have to worry about understanding it in Chem 1 and Chem 2.
Gotcha. I'm pretty much getting it.
Finest
Now I know.
kind.
Took a while though.
All right. To find the density, if you have the mass and you have the volume, If the mass of the object is 35 grams and it takes up 7 cubic centimeters, by the way, write this down right now. 1 cubic centimeter is equal to 1 milliliter, which is equal to 1 cc. 1 cubic centimeter, 1 centimeter cubed is equal to 1 cc, cubic centimeter, which is equal to 1 milliliter. They're all the same volumes. So I have the mass, I have the volume. Look at my triangle. I'm going to take the 35 grams, my mass. I'm going to divide it by my 7 centimeters cubed. And I am going to get an answer of 5 grams per centimeter. You notice the labels didn't cancel out. So the label for density is going to be grams per centimeter. Questions, guys? All right. If I need to find the mass, okay, by my density triangle, if I take my density, multiply it by my volume, I will get my mass. So I have the density. My density of my object is 1.52. The volume I determined to be 25 milliliters. How much is the mass of that stuff? So again, by my triangle, I know if I take my density, multiply it by my volume, I'm going to get the mass. So if I take 25 and multiply it by 1.52, I'm going to get a number, and that's hidden for me right now. Somebody tell me what the number is.
38.
38 grams? Are we at 38 grams?
Yes.
I'm sorry, it's hidden on my, the bar for my Zoom is hiding it. Let's look at this another way, okay? Remember, we said mass is in grams, right? Right? The label for mass is grams, okay? Oh, here, I'm sorry. Sorry. Let me backtrack here. I'm sorry, I was trying to do the other problem. The label for my density is grams per milliliter, right? Right, guys? If you don't want to
Yes.
do the triangle, this is another way to do the problem. If my density label is grams per milliliter and my volume is in milliliters, if I multiply those two together, milliliters cancels out and I'm left with grams. Does that make sense? In both instances, you're multiplying the density by the volume. Both problems, you're doing the same thing. One, you're using the triangle to just plug things in. The other one, you are using the labels. Either way will work. Since density is grams per milliliter, if I multiply that by the volume, that will give me the mass. In this case, it was 38. My mass is 35 and the density is 1.2 grams per milliliter. What is the volume? I have mass and I have density. By looking at my triangle, if I divide my mass by my density, I am going to get my volume. So I have the mass, I divide that by the density, and I end up with my volume. Again, I can't read that. 29 milliliters. All right, let's look at the labels. If I have 35 grams and I multiply it by the density, look at the labels. Don't the labels, if I multiply the 35 by the 1.2, don't I have to also multiply the labels? And I would get grams squared over centimeters cubed. That is not volume. I need centimeters cubed on its own. So what I do is I take the grams and I divide it by 1.2 grams per milliliter. Remember, in fractions, when you divide by something, it's like if you divide by a fraction, you multiply by the reciprocal. So in effect, what I'm doing here is I'm taking my 35 grams and I'm multiplying it by 1 milliliter over 1.2 grams. Math-wise, I'm dividing the 35 by 1.2 and I'm ending up with the 29. Are these easy problems, guys? Fairly easy problems?
Yes.
Nothing,
Yeah.
nothing that's gonna tax, nothing's gonna tax you too much, right?
Right.
Hope not.
Okay, let's see where we're going from. Problem. A graduated cylinder weighs 109.850 grams. Liquid is poured into the cylinder until the volume of 15.6 milliliters is read. The cylinder is reweighed and found to be 122.174 grams. What is the density? Now, when you do liquid densities, when you do an experiment for liquid densities, you can directly measure the volume. All you got to do is pour it into something that you can read. Make sense? So you can directly measure what the volume is. In this case, the volume is 15.6. Unfortunately, you can't pour the liquid on the weigh pan. If you pour the liquid on the weigh pan, it's going to go all over the place. So you're not going to get the weight of that 15.6 grams. You need a container when you are doing the weight of a liquid. So what you have to do is you have to do an extra step. You got to weigh the empty container, then pour the liquid in, measure the volume, then reweigh the container with the liquid. Rosina, you out there, Rosina?
Yes, sir.
Okay. Are you seeing this problem?
Yes.
All right. The question is, what is the density?
Yes.
In
So
order to,
density would be mass by volume. However, we need to first figure out the mass of whatever it is that we are pouring. So the total weight, the total mass is 122.174, but the cylinder itself weighs 109.850. So when we deduct, the mass would be 12.324. And so applying the formula, the density would be 0.79.
not quite.
Not quite.
Not
Okay.
quite. You are almost there. Your explanation was excellent, Rosina, until your final answer. Rosina,
Yes.
how many sig figs in 15.6?
3,
How many sig figs in 12.3234?
5.
So if you have dividing 3 by 5, how many sig figs does your answer have to have?
You take the smaller number, which is 3.
So instead of being 0.79, it's going to be 0.784. That's the only problem I have with your explanation. She
Okay.
did it absolutely correctly. What you got to do is, you know, the weight of cylinder and liquid, you know the weight of just a cylinder. Subtract the two, you get the weight of the liquid.
That's where I always go wrong. I always got to remember that. You got to take the lowest sig fig from the, you know what I mean?
Absolutely, Hunter.
Mhm.
Practice. You
But
do
where
it.
does the 4 come from?
Which 4?
Like the 4 in the answer, the 7, 2, I mean,
Did
7,
I
8,
do the
4.
math wrong?
Because when I did the
Yes.
math, I just got 0.79, no other numbers.
Yeah, same, because
Switch the digits in the weight there. It's 12.324, not
324.
234.
So with that, would you put an estimated digit for a zero?
Wait. Time out. What did somebody just say? Did I do a calculation error here?
Yeah, you just switched two
No, it's
digits.
a typing error. on the answer for the first part, you did 12.234 and it should be 324.
Yeah.
Oh. Who did that? Who found that? Who's the first one that said it?
Not me.
Who's me?
I
need a
think it might
name.
be Kaylin.
Kaylin?
Yes.
Kaylin Jones.
Yeah, that's
got-
me.
You got your point.
Yay.
Okay. Okay, so let me.
So it does come out to 0.79 like Rosina said, but it would be 0.790, right?
Correct.
For the sig pigs?
So this,
Okay.
this number should be 324.
Yes.
And this should be 790. Okay, I can live with that. Okay? We good?
Yep.
A block of aluminum measures 1.65 centimeters on the side. If the density of the aluminum is 2.7 grams per milliliter, how much is the mass? Kaylin, since you were so
Yes.
smart last time, yeah, this will teach you to find errors.
I spaced out for a minute. What are we doing?
We're doing the new problem.
Okay.
All right, we got a block of aluminum measures 1.65 centimeters on the side. If the density is 2.7 grams per milliliter, how much is the mass?
Mass is density times volume. So calculator out 1.65 times 2.7
Okay, is this the volume?
is 4.445, but
Kaylin,
only
hold it. Kaylin, stop for a second. Is 1.65 the volume? I think I've stunned her. Guys, somebody. Kaylin is now muted. Guys, somebody tell me, is 1.65 the volume of the block?
No, it's a
No.
measure of one of the.
not.
So how do I get the volume?
Gotta get the area first.
Not the area. How are you going to get the volume of a cube, a block? If you know what,
Length times width times height.
so what's the length times width times height?
1.65 cubed.
1.65 times 1.65 times 1.65.
4.492125.
I've got 4.49. That's what I came up with.
That's what I got also.
Good enough. So I got 4.49. That is the volume of the cube. Now, if I know what the density is, all I got to do is multiply it now. Take that milliliters that I have, multiply it by the density, and I get 12 grams. Questions? One last problem. A Greek scientist way back came up with the discovery that if he was going to take a bath and he put his little tush in the bathtub, he observed water coming out, and he came up with the idea that the volume that came out was equal to the amount that he put in. So his body put entirely in that bathtub would displace the same volume of water. We can use that, guys. We can use that. I have 44.99 grams of an irregularly shaped metal. I fill a graduated cylinder to the 45.00 milliliters mark. When I put that irregularly shaped metal into the water, the water level rises to 51.30 milliliters. Now remember what Archimedes said. He said that the amount of water displaced equals the volume of what gets pushed into the water.
Mhm.
So if that's the case, can you tell me what the volume of my irregularly shaped metal is? How to get it?
Sorry, can you repeat that question?
Okay. Archimedes said, if you put an object into water, that
Right.
object will displace the same volume of that water as it has. So in other words, I put the irregularly shaped object into the 45 milliliters of water, that displaced water to the 51.30 milliliter level. Can you tell me how to get the volume of the metal now?
Wouldn't you just subtract 51.30 by 45?
Exactly.
Okay.
So if we have an irregularly shaped object, we can't measure its volume. We have to do that indirectly. So we do that by filling up a graduated cylinder to a certain level, adding the object, and seeing how much the water rises. The difference in the two is going to be the volume of the irregularly shaped object. So in this particular case, I'm going to take final volume minus my initial volume. This gives me 6.30. My substance, my metal weighed 43.84 grams. To get the density, I divide it by the volume. I get 6.95 grams per milliliter. Remember 6.95.
Hey, Professor, I've been using my phone as a device, but I switched it to the computer, so I'm not late. I've been here since this
Okay.
call.
Okay.
Thank you.
The answer to our problem was 6.95 based upon this series of densities. What would you have to identify?
Antimony.
Look closer.
Zinc.
Zinc. 6.95 is closer to 7.13 than it is to 6.6.
Can you go to the next slide again? Where did
This
you get the 43.84?
was in the problem. Yeah.
Oh, but it said 44.94.
Why do you guys find errors? Who is that? Who is
Mariah.
that? I'm sorry?
Mariah.
Mariah.
Lebeau.
Thank you. You got yourself your first extra credit point. Now I got to do that. Guys, I'm sorry. I am not a detailed person. You're going to find these kind of mistakes all the time. Actually, it works out better.
Can you hear me?
Yes, I can.
I was working on some of the Pearson stuff last night, homework 2, and I found a couple of
Okay, Andrew.
I know we'll
Hunter.
talk about it later, but yeah, there's a couple things that I saw in there that was like glitchy.
Hunter, again, point those out at some other time.
Right.
I can't be correcting things during lecture, okay?
No problem.
These basically are the types of problems you are going to work when you work a density problem. Do I have any questions on density? Fairly
Professor, I
simple.
have a question in regards to sig fig for this calculation, the 44.94 divided by 6.3. So in the calculator, it is 7.1333 unlimited. But because 6.30 are 3 significant figures, so is that the reason we are going to limit to 7.13? Okay, thank you.
Exactly. Anything else, ladies and gentlemen? Okay, the next one is, do you want to see a cartoon or not? Silly cartoon.
Sure.
Sure, love
Down,
cartoons.
down.
Let's see if
I
I can
vote
find,
no.
I'll see if I can find it. Nope. Okay. I'm not sharing yet, am I? Oh, I'm not sharing. Very silly cartoon. Okay. Stop share. Share screen. Share sound. Boom. There we go.
Eureka! This unit is divided into 3 programs. The program you're about to see is on volume and density. This will be followed by buoyancy. And the third and last program in the unit will be on convection itself. But our story begins with volume and density. What does the word volume mean? What does the word density mean? Well, imagine that you're a junk car dealer and you want to send these 8 old wrecks to the steel yard for recycling in this container. The only trouble is they're full-size cars and they won't all fit in. If only they were tiny little compacts, there'd be no problem. But they're not. That's only a dream, so it's time for the car crusher. But wait, how small should you crush them so that they'll fit exactly into the container? Well, how big is the container? 4 meters? No, that's only its height. What you need to know is how much space there is inside it. Look at it this way. The outsides of the container make up a sort of envelope. What you need to know is how big the space inside this envelope is. Or rather, if we use the Greek word for envelope, how big the volume is. Because that's all the word volume means. How much space a thing envelops. The easiest way to work out the volume of something like a box is to measure not only its height, but also its length and its width. And then multiply all these together. 4 times 4 times 4 equals 64. The container has a volume of 64 cubic meters. And since you have 8 cars that you want to fit into it, you'll have to reduce the volume of each car to exactly 1/8 of 64 cubic meters, which is 8 cubic meters. In other words, you'll have to crush each old wreck into a cube measuring 2 meters by 2 meters by 2 meters. So start compacting each car until it takes up exactly 8 cubic meters worth of space. There. You now have 8 compact cars. Your dream has come true, and they all fit neatly inside the container. But what's all this got to do with density? Well, the word dense comes from the Greek dasos, which means compact. So a car crusher, which turns full-size cars into compacts, is really a sort of density machine. It takes a car with a mass of, say, 2,000 kilograms and squeezes these 2,000 kilograms into a much smaller volume. So one way to increase the density of something is to keep its mass the same, but decrease its volume. You can also do it the other way around, of course. If we look at the density of the container, we see that when it holds 2 2,000 kilogram cars, it's a quarter as dense as when it holds 8 2,000 kilogram cars. In this case, you increase density by keeping the volume the same, but increasing the mass. And now you know the meaning of the words volume and density. Don't you? Where did he go? Oh, how dense can you get?
Okay. Actually, believe it or not, that had a lot to do. The reason I like that is because he goes through and tells you how to manipulate the equation. If you want to increase the density, you can do it by two methods. Keep the mass the same, decrease the volume. Or you can increase the mass, but keep the volume the same. That's really what I really wanted to drive from here. We got one more equation to deal with before we get on to history. And that is temperatures. Okay? Guys, there are three systems for measuring temperatures. One is Fahrenheit. As it says there, I will try not to use the F word ever in chemistry. The second one is Celsius, and it's also called centigrade. Guys, you will hear me use centigrade and Celsius interchangeably. They basically mean the same thing. The third temperature scale is called Kelvin. It is the absolute temperature scale. It is the best one to really use if things come down to it. Now, the real neat thing is you can relate temperatures to one another if you look at a physical phenomena. If we look at where water freezes and where it boils, we can relate one of these scales to the other. Let's do the easy one. Look at the difference between Celsius and Kelvin, okay? If we are at 0 degrees Celsius, we're at 273 Kelvin. Go to the boiling point, 100 degrees Celsius is what water boils at. Kelvin, it's 373. So the difference between these two scales is you have to take your degrees Celsius and add 273 to them. Only difference. Degrees Kelvin equal degrees Celsius plus 273. Now, if we want to look at the relationship between Celsius and Fahrenheit, we don't start off at the same place. Water freezes at 32 Fahrenheit, but it freezes at 0 Celsius. So we have to take into account. The first thing we have to do when we're doing this, figuring out the relationship, is we have to add 32 to Celsius temperature. Then look over here. The amount of heat needed to raise Fahrenheit from 32 to 212, the same as the amount of heat needed to raise Celsius from 0 to 100. Are those energies the same? Remember,
Yes.
we're taking freezing water to boiling water. The amount of energies is the same. So if that's true, then we can relate. The difference between 212 and 32 is 180 degrees Fahrenheit. Between 100 and 0 is 100. So if I want to relate degrees Fahrenheit to degrees Celsius, I divide the Fahrenheit degrees by the Celsius, and I get Fahrenheit is equal to 1.8 times the Celsius degrees. But you got to remember, I offset that by 32. So the real formula to change Fahrenheit into Celsius is F is equal to 1.8 C plus 32. So to reiterate, if I'm changing Kelvin, if I'm changing Celsius to Kelvin, all I got to do is add 273 to it. If I'm changing Kelvin to Celsius, I subtract 273. If I am changing Celsius to Fahrenheit, what I have to do is I have to take 1.8, multiply that by the centigrade degrees, and add 32. If I'm doing the opposite, the first thing I have to do is if I'm taking this, I'm algebraically solving for T centigrade, I subtract 32 from both sides, then I divide by 1.8. So if I have Fahrenheit temperature, the first thing I have to do is subtract 32, then divide it by 1.8, I get centigrade. The average human body is 98.6 degrees Fahrenheit. Express this temperature using the Celsius and Kelvin scales. I get 98.6 minus 32 divided by 1.8. My answer is 37.0. Anybody have a problem with this answer? Hunter, you're the one that was concerned with sig figs earlier. Do you have a problem with this answer?
Let me see it. I'm trying to squint.
Professor, I'm so confused.
This is Kate.
Yeah.
Hold on.
Hold on, Kate. Let me get Hunter to answer this question. All right, let me throw it out to you guys.
I see the question, but where's the answer at? Because if I can see it, I can tell you if it's
right here.
That one? That's three sig figs right there. No, it looks good. Yeah. Well, actually, no, it should just be 37.
Is 32 an exact number? Hunter. Yes. Is the 1.8 an exact number?
No. Or yes.
Yep. Yes, it is. Because it's exactly 180 degrees Fahrenheit equals exactly 100 degrees Celsius. So the 1.8 is an exact number. When you are doing,
and that's 2 sig figs, but the answer 37.0, that's 3 sig figs, right?
Again, would you agree, Hunter, that the 32 and the 1.8 are exact numbers?
Yeah.
If they're exact numbers, they do not determine the amount of sig figs.
Oh, forgot about that. So yeah, then it's right, because then 98.6 would be what you want to base it off of.
Yes.
Okay.
Now, Gate, what are you confused about?
I'm sorry. So I'm looking at the question. So the 98.6 is the Fahrenheit. So is the 32, I'm assuming, is the average Celsius body temperature. I'm confused.
No,
I don't understand.
Gate, here are the formulas. You're given Fahrenheit temperature. You want Celsius. So you just plug it into this formula. Fahrenheit temperature minus 32 divided by 1.8 will give you Celsius. That's all I did here.
Okay, so the general formula is the 32 divided by 1.8, and you're just plugging in the number given.
Yes.
Okay.
Now, in order to get the degrees Kelvin, I have to add 273.15 to my Celsius temperature. In this case, I get 310.15, or the more correct answer, 310.2 K. I have to use the 273.15 because my temperature goes out to one place past the decimal. I don't want my 273 to limit my answer. Let's do a problem, guys. Normal body temperature for a dog is approximately 102 degrees Fahrenheit. What is this equivalent on the Kelvin temperature scale? For right now, all you need to do is write down 104 Fahrenheit. Those are all the formulas you need. I'll give you a couple minutes to do this.
104 or 102?
102, I believe.
Okay.
102 is what it says.
Okay, I thought you said 104. Sorry.
102. If I did say 104, I meant 102.
Okay.
Be right back.
Okay, guys, I just have a question.
All right, shoot.
Is this Terry?
Yes, it is.
Yo, Terry, man. so the top, the T K equals TC plus 273. That's to find the Kelvin
That's to find
for
your
Celsius.
that's to find your Kelvin. So you plug in your Celsius temperature, add 273, then you get your Kelvin.
That's only if the question is asked, 37 Celsius, what's the Kelvin scale, right?
Correct.
And what's
So in this question, we're converting 102 Fahrenheit to Kelvin. So first you have to go to Celsius, then Kelvin. You feel me?
wait. Okay, hold on. So I don't see the question. Where's the question?
Well, he changed the slide.
Yeah,
The
he
question
changed the
that
slide.
Yeah.
Okay.
The question was, oh, sorry, Jennifer, you go ahead.
Oh, no, you're fine. Yeah, the question was, we have 102 degrees Fahrenheit trying to change it to Kelvin, but we have to change it to Celsius first, which is the temperature of Fahrenheit minus 32 divided by 1.80. Once you get,
I'm
Mhm.
sorry, go ahead.
No, you're fine. I was gonna say, once you get that number, then you plug it into the formula above, the temperature for Celsius plus 273.
So basically, we can't jump from the Fahrenheit to Kelvin. It has to go in like a step process. So
Yeah.
Fahrenheit, Celsius,
Yeah.
then Kelvin.
Yeah. Mhm.
Absolutely. Who's making that? Who's doing this explanation?
It was a combination of me and Terry. Jennifer and Terry.
I'm sorry. What I heard was damn good. Was right on. So what answer did you come up with?
B.
B.
And you would be right.
Can we see a fine example, if you don't mind, a demonstration or something?
Demonstration?
Can you show us the problem, or just so I can see it visually, if you don't mind?
Okay.
I don't know how, but
I'll go through and okay. T Fahrenheit is equal to 1.8 T centigrade plus 32. Okay, Fahrenheit is 102, is equal to 1.8 T centigrade plus 32. 102 minus 32 equals 1.8 TC. That would be 70. 70? Looks right.
Yes,
Equal
sir.
to 1.8 TC. Divide both sides by 1.8.
You're looking at 38.
You're looking at 38.8.
Mm-hmm.
you said divide
Okay.
each side by 70, right?
Sorry, what?
Divide each side by 70, you said?
No,
By
divide
1.8.
each side by 1.8.
1.8.
Okay. Then to this, all I'm going to do is add 273.2. And this adds up to be 312. Okay. All I'm doing here is plugging numbers in.
I have a question.
Answer. I've got an answer.
So rounding is okay in this instance.
I didn't round.
Professor, my answer is also 38.9, not 38.8, because it's on the calculator is 38.88. And if there are 3 sig figs, then it's 38.9.
Okay, you got me.
Shouldn't it be 2 sig figs though, because of the parentheses?
No, because 102 is 3 sig figs, and 32 and 1.8
No,
don't matter.
it should be 102 minus this is going to be 32. Remember, the 102 is accurate to the units place. So when you subtract the 32, it loses a sig fig. So 102 minus 32 is going to give you 70. Then you divide the 70 by 1.8, that gives you 38.888 something, or 39. You add the 39 plus the 273, you get 212.
So here's the question, Professor, because it's a whole number. Because they were talking about the sig figs and whatnot. I don't know why. I just don't seem to comprehend when it comes to
You're not getting, are you not getting the formula, or you're not getting the sig figs?
I don't get the sig figs, to be honest.
All right. Right now, this 102 is accurate to the units place. When I subtract 32 from it, the 70 that remains is still accurate to the 0 place. The 70 is 70 with a decimal point. That 0 is significant. I then divide 70 with 2 significant figures by 1.8. I get 38.8. Since it has 2 significant figures, that gets rounded up to 39. Add that to 273. My final answer is 312.
Okay, and we're getting the 2 sig figs from the general 70 or the 1.8? Because I know you said something about the smaller number.
No, you're getting it from the 70.
The 70. Okay.
The 1.8 is exact. The 32 is exact. So those are never going to dictate what the sig figs are.
Okay.
Okay.
Awesome. Thank you.
Any other questions there? Okay. Unfortunately, ladies and gentlemen, you hooked yourself into a professor that is a history nut. So this is the way I like to introduce you into the history of the atom and what the atom's all about. So we're going to get into the history of atomic structure. And first of all, we're going to get back element, compound, or mixture. Terry, salty water, element, compound, or mixture.
Mixture.
Elizabeth, hydrogen, element, compound, or mixture. Elizabeth?
I'm here. Can you hear me?
Yes. Hydrogen, element, mixture, or compound?
Element.
Okay. Hydrochloric acid. Fabiana.
Mixture.
What's your second best guess?
Compound.
Compound.
It's a compound because I've got hydrochloric acid. I've got a mixture of 2 things making this. What about air? Do I have, look in here.
Mixture.
I think it's a mixture, Professor.
You think so? You think? All right, how about a diamond?
Element.
Ooh,
Compound.
no.
Mixture, probably.
No, a diamond is completely composed of only carbon.
Oh yeah, that's an element then. Oh yeah, because we have the pressure.
It's an element. And what's this last thing?
Compound.
It's a what salt?
Compound.
Table salt is a compound. All right, we're going to go through the brief history of atomic structure. We're going to give Dalton's contribution, Proust, Thomson, Rutherford, Planck, and Bohr. Yes, ladies and gentlemen, you will be responsible. You will be responsible for knowing who did what. It's not going to be, do not overwhelm yourself studying this. There are going to be other things you need to study, but it will be asked on the test. We go way back. There's a guy by the name of Democritus. And Democritus was the first one who said that matter was composed of small particles. And he called these things atomos. He was opposed by another Greek scientist, and the matter was thrashed out, and unfortunately, Democritus lost. So for years, we went on thinking that the entire substances on the earth were made up of things like fire, earth, water, and air. Later on, took all until the 1800s, John Dalton proposed his atomic theory. And this atomic theory had 5 basic parts to it. Basically, what he was trying to do was he was trying to correlate rules for what things were made out of. His first thing, he said, matter's made out of indivisible particles that he named atoms after Democritus. He also said atoms can't be destroyed or created. Atoms are unique to one another. They're unique to one another because they have unique properties that are fixed to that element and to no other element. Atoms can combine to form compounds. He said an atom is like a billiard ball. By that he meant when they bounced, when they hit into one another, they rebounded, just like a billiard ball did. And last, he flew in the face of the prevalent science at that time. Everybody there was practicing alchemy. They were all trying to make gold from lead. Dalton said it can't be done.
It can be done.
Radioactively, yes.
Yep.
But not chemically. Now, guy by the name of Goldstein, he was the one that found that there was radiation in a gas discharge, and this positively charged radiation was later funneled down to the discovery of a proton, which led J.J. Thomson in 1897. He used cathode ray tubes. Guys, televisions used to be made of cathode ray tubes. They're nothing more than a tube that allowed transfer of electrons from one side to the other. And basically, what J.J. Thomson was able to do was he used these big, long cathode tubes, and he put positive magnets on one side, negative on the other, and he was able to determine that the atom was composed of positive and negative entities. He viewed the atom as a plum pudding. Now, I use that analogy. Has anybody ever eaten a plum pudding in their life?
No, I don't want to.
No.
That's kind of interesting.
Well, yeah, once you look at it, you don't want to eat it. It's kind of like an amorphous white mass that has plums in it, just stuck in it. Has anybody ever eaten a Jello fruit salad?
Yeah.
Yes.
Yes.
All right, you know what they are at least.
Mhm.
Believe me, I wouldn't eat one to save my life either.
Is that like a
Basically-
Bandersnatch?
Yeah, I
Thank
can't.
you.
I'm vegan.
Thank you, guys. Just to give you a visual of what J.J. Thomson was proposing for the atom. Think of it like a Jell-O fruit salad. You know, you start to set the fruit salad. You put the Jell-O in the refrigerator. It starts to get a little bit solid. Then you start to dunk the fruit in there so that the fruit gets separated from one another. And so
wasn't he the guy that proposed the empty space, like how in atoms are comprised of a lot of empty space?
No, that's Rutherford. I'm going to get to him in a second.
Oh yeah, that's Rutherford.
So J.J. Thomson said his view of the atom was you had these positive things and these negative things that were just shoved into this gel-like matter. Curiously enough, Hunter, we run into Ernest Rutherford in 1911, about 10 years later. What he did was he did a famous experiment called the gold foil experiment. What this did was it disproved Thomson. And he came up with a new hypothesis that the atom was composed mainly of space. Let's see if I don't have the picture.
Do you
Sorry,
want to know
I thought I had the
weird,
picture.
a weird fact about that?
What? Go ahead.
They say that if every human being, like if the space in between our atoms were taken away, every human being could fit inside the size of a sugar cube.
True. That's absolutely true. All right. Let's see if I can describe this. I'm going to hopefully pan back here. All right. You see, I have a piece of paper here. Okay. What Thomson said was that if I have this foil, this gold foil here, since this gold foil, it's composed of a metal, an element, so it's got this gel matter and it's got protons and electrons just kind of stuck in here. So this is kind of a solid thing. So if I shove a series of electrons at this, I'm going to expect the electrons to bounce back at me. When Rutherford did his experiment, he found that most of the electrons went through. Because some bounced back, but most of them went through. Because of this, he hypothesized that, well, some bounced back, so some of them must have hit off a dense center of the gold. But since most of them went through, he basically said that most of the atom is composed of space. So he further went on to delineate what he was saying. He basically was the first one to describe a nucleus of an atom. And basically he said that the nucleus is going to be essentially the mass of the atom. It's going to be positively charged. And what Rutherford said was that electrons fly in space around this nucleus.
But electrons and protons still have a very small amount of mass, right?
Yes. Okay. But the mass of an electron is about 2,000 times less than the mass of a proton.
Oh, damn.
Okay. So that is, stop. That is what Rutherford did. Rutherford was responsible for determining that he determined that there was a nucleus and that the atom was composed mainly of space. And he also determined that the nucleus is positively charged. Around this time, another scientist by the name of Max Planck, they were discovering, all of the scientists at this time were discovering what was known as the ultraviolet catastrophe. Pretty much up until the turn of the 20th century, everybody felt it's all solved. Waves act, energy acts like waves, and there's nothing that I need to worry about, because if I want to know the energy, I'll just calculate it like I would the energy of a wave. What happened is they discovered the ultraviolet catastrophe. According to classic theory, as the temperature increases, the wavelength of the energy should increase to infinity. What that means to you is that every time you open an oven door, you should get blasted by UV radiation. It doesn't happen. What Planck did was Planck said that energy is not wavelength in nature. He said that energy is composed of little packets of energy. To give you an analogy, classic wave theory would be like walking up a ramp, gradual. You get a gradual increase of the energy. Planck's quantum mechanics says that you're not gradually increasing the energy, you're increasing it like you're walking up steps. Little packet of energy, another little packet, another little packet, another little packet. So Max Planck is responsible for something called quantum mechanic theory. And he developed another equation called E is equal to h nu, where E is equal to the energy of the particle. H is a constant. Funny enough, it's named Planck's constant. When you get famous enough, they get the name constants after you. And the V is the frequency of the light. All right. Who likes fireworks? Jennifer, do you like fireworks?
Yes, I like fireworks.
Oh, wonderful. You're there every 4th of July, every New Year's Eve. You're out there looking at the fireworks, right?
Yeah, my birthday is actually the day after 4th of July, so it's right there.
Oh, good for you. My aunt's birthday was on the 4th of July.
Nice.
Basically, the way fireworks work, you take energy and you put it into a chemical. Okay? In other words, you send these fireworks, you have sent them up, and you make this boom. That boom for the fireworks excites the electrons within the particular molecule. Okay? What happens? It excites the electrons get really, really excited. Then the energy from the explosion goes away. And you've got these excited electrons that go back to where they normally were. When they go back to where they normally were, that releases energy. That's the energy you see when you're looking at fireworks. That's the light color. Now, because every chemical gives different colors, this means there are different energies that are involved with the electrons that are floating around the nucleus. Niels Bohr proposed, okay, what I'm going to say is there are very discrete energy levels, and the electrons can be in these very discrete orbits. So I'm going to have one orbit that's real close to the nucleus, another one that's a little further away, another one that's further away yet. So Niels Bohr's version of the atom looks something like a solar system. So he combined both what Rutherford was saying and what Planck was saying, and said that the electrons travel in specific energy levels called orbital. The energy between these two orbitals is the quanta of energy, and the higher the orbital, the more the energy. Last guy I think I'm going to talk about is a guy by the name of James Chadwick. What he did was he discovered something called the neutron. Now, riddle me this, ladies and gentlemen, and I'm going to end on this point. If we have all these positive things stuck in the nucleus, they're all positive, why doesn't the nucleus explode? What would keep all these positive things together? You guys have worked with magnets.
Nuclear, like some sort of nuclear strong force, or what do they call it? The weak force, strong force thing?
The neutron has a negative charge.
No, it doesn't have a negative charge. It has
It's
a
a
neutral
neutral charge.
Neutral charge.
Hunter, you're almost there. Okay.
When it has many
Sort of
positive-
electromagnetic force or something.
No,
I
it's not
forget.
an electromagnetic force. It is
Gravity?
I'll look it up for you. It just, the term has lost me. There is a force that keeps the nucleus together. Now, if you just have positive things in there, it's going to explode. But if you intersperse the positive pieces with neutral ones, that separates the positive charges from one another.
I got it.
Okay.
1 second, Gaith. I need to get this explanation in.
Oh, that wasn't me.
I'm sorry.
That was
Sorry.
Omar.
Omar, 1 second. I will get to. Sorry, Gaith. All right. So you have these neutral things that are separating the positive charges away from one another. Now, does one body have an attraction for another body? And I don't mean a male to a female. If you have one thing like the moon, does the moon have an attraction for the earth? And does the earth have an attraction for the moon?
Yes.
Yes.
You know that because of tides. So if you have two objects, there is a force that attracts one to the other. It's this force which keeps the nucleus together. So we have neutrons to keep the nucleus together. It separates the protons enough, and it adds these forces between itself and protons to keep the nucleus together. Omar, question.
Oh, my question was, they were all negative in this. So is it gonna explode too, or it's not?
What are we talking? The electrons?
Yes,
You mean the electrons on the outside?
and the inside.
I'm sorry.
No, on the inside.
There are no, Omar, there are no electrons on the inside. Remember, remember that Rutherford said that all the electrons are outside of the nucleus. There's a very hard mass in the center of the atom. That hard mass contains protons, but no electrons. The electrons are flying outside of it. Okay, Omar?
Oh, okay, I see.
That's kind of an interesting year, 1932. I mean, that gets closer to 1945 with the first atom bomb, because they couldn't have had that research without Chadwick's discovery, right?
Right, absolutely, because you need neutrons to fire the neutrons at the uranium to set the chain reaction going. Ladies and gentlemen, that's all I have for us right now. We will pick up with the parts of the atom on Tuesday.
All right.
Any
I'll see you on
questions?
Tuesday.
Any questions? We went through the history tonight, we went through density, and we went through temperature. Any questions on that stuff?
Lab after this is for 7:30 instead of 7.
7:30, always will be at 7:30. I can't get this recorded fast enough.
That's fine. Perfect.
Thank you, Mila.
Trying to show you guys his tattoo this whole class.
Oh, good. Where's his tattoo? Let him show me.
Here, show him your tattoos.
It's an atom.
It is. Can you see it?
Look at the guns on that kid.
Oh, and then my other son's trying to show off his too.
Ah,
Those are cool.
absolutely.
So cool.
Dynamite, guys. Dynamite.
No.
Guys, we got to end. I got to get this
All
recorded.
right, say
I got to
bye.
get this recorded so I can start my lab up, okay?
Professor, I just had a quick question, if you don't mind.
Gates, quick.
So just to ease back, I know you have to go. So basically, for the sig figs, you're basically choosing the least number or the smallest number when it comes to
Gates,
picking the
Gates,
yes,
Gates.
yes.
What I want you to do is I want you to go back either to the PowerPoint or I want you to go to the survivor guide.
Okay.
I want
Yes,
you to
sir.
read that. I want you to read those over. I want you to study it. And then I want you to re-ask that question to me on Tuesday at 5 o'clock, okay?
Okay. Sounds good.
Because I need, I
No worries.
Gates, the
Yes.
other thing is go to organic tutor, organic tutor. Type in organic tutor, comma, significant figures. Or go to Khan Academy, KHAN Academy, and look through, go through one of those videos. I have one that I have set up in the online outline. Okay, Gaith? I
Yes,
want
sir.
you to do that. I want you to study that before next Tuesday. All right? Did you
Yes,
have a simple question or did you have an overall question?
No, that's it. Thank you.
Okay, good enough.
Thank
Guys,
you,
I will
Professor.
see you in about a half an hour. Any other questions?
No, but I'd like to apologize for my Zoom disconnecting while I was supposed to be answering a question, so.
No need. No need,
RIP.
Kaylin. No need.
Thank-
I rolled with it, okay?
Okay,
Take care.
thank you. Good
All right,
night.
Professor. Love you. See you.
Good night. You take care, guys. Rosina.
Thanks, sir. Stay safe.
Mary, we good? We good? Neela,
Yep, good.
we're good? Leandre? Leandre is gone, so we don't have to work. Rosina, you good? I will see you later on then, okay? Take care.